now we're going to look at a couple of application problems that are going to require us to use our new rules, quotient rule and product rule for finding derivatives. So in the first problem here, we are given a function that approximates the mortgage rate. T equals 1 is T equals 0 corresponds to the first week of May in 2010. T is measured in years. And our first question is, what was the average 30-year fixed mortgage rate in the first week of May in 2011? So when T equals 1. So notice here we're not asking for a rate of change. We're not saying how fast it was changing in part A. In part A, we just want to know what the mortgage rate was in 2011. So I'm going to take the function as is, and I'm going to put a 1 in place of T. And I get about 4.7% when I put that into the calculator. So the fixed mortgage rate in 2011 was 4.7%. We want to know how the mortgage rate was changing during that particular time as well. So if I want to know how fast the mortgage rate was changing, was it going up? Was it going down? Was it going up by a lot, up by a little? How quickly? How fast was it changing? So we're going to find the derivative. We want to know how fast something is changing. We want to find the derivative of our function. We have a fraction, so we're going to use our quotient rule. So it's going to be the denominator as is times the derivative of the numerator, which is 0. Remember our constant, if we take the derivative of that, we get 0. Minus the numerator as is times the derivative of the denominator. So that's going to be our power rule. So in the denominator, t squared, that would be 2t. And then here we have a constant times x, so we know the derivative would just be the constant. So 0.31. And then, of course, the derivative of the constant term that has no variable in it, we know that's 0. So we'll stop there. All over the denominator as is, but we're going to square it. All right, so we want to use this, so I'm going to simplify it a little bit. And remember, these are really nice problems when we have a constant in the numerator because 0 is the derivative and 0 times everything else is just 0. So we know all of this becomes 0. So we end up with negative 55.9 times 2t minus 0.31 all over that denominator squared. All right. So I'm going to use this to actually answer the question. It says, how fast was the mortgage rate changing in the year 2011? So we're going to put t equals 1 into our derivative. All right, now I went ahead and I put parentheses everywhere I had a t and put a 1 in the parentheses. And I used brackets so that there wouldn't be too many parentheses floating around for those outside parentheses. Okay, we're just going to throw all of this into the calculator, and then we're going to see what is our rate of change in 2011. And I get negative 0.668. And if I round that to the nearest 2 decimal places, I get negative 0.67%. All right, so how is the mortgage rate changing in 2011? It looks like it is decreasing, so it's going down by 0.67%. We'll think of it as a fraction, like as a slope. We'll put it over 1. So what we're saying here, as the year increases, so as we increase by a year, it looks like the mortgage rate is going down by 0.67%. So I'm going to put here that looks like the rate, that mortgage rate is decreasing at that much per year. Okay. All right, so remember one little thing here is the change in the mortgage rate, the change in the function values divided by the change in years. And that's how we're interpreting our answer kind of in terms of that slope. For our next example, we're looking at a demand function for sports watches. It says here that the demand for these watches is given by the following function, d of x equals, and we have a fraction. X is measured in units of 1,000, so we'll keep that in mind. And the output tells me the unit price in dollars. So the first thing we're asked to find is the derivative. So d prime of x is equal to, so since we have a fraction, we're going to use our quotient rule. It's the denominator as is times the derivative of the numerator. Since the numerator is a constant, the derivative of a constant is 0. Minus the numerator as is, so I'm going to put 50, times the derivative of the denominator. So I'm going to use the power rule for the derivative of just what's in that green box. So we're going to do 2 times 0.01, so that gives me 0.02, and reduce the power by 1, so I get x. Remember the derivative of plus 1, that term right there would be 0, and I don't put plus 0, because we know we would just end up with 0.02 times x. All over the denominator squared. All right, so let's simplify. Once again, just too easy not to, because the denominator times the derivative of the numerator, well, we know that anything times 0 is going to give me 0. So that's really nice and easy. Let's go ahead and multiply these two values together after the minus sign. 50 times 0.02 would just give us 1. So we're left with just minus 1x, or just negative x. Okay, and then all over the denominator squared. And once again, I'm not going to actually square that out. I'm just going to leave it as is. Okay, so there is our derivative. Okay, so for part B, we're asked to evaluate the derivative at some particular values and interpret the results. For part B, we are asked to evaluate the derivative at different quantities. So here, if I'm plugging a 5 into the derivative, we're talking about 5,000 units being demanded. And we want to know how this affects the price. Okay, so we're looking for change in price divided by change in quantity. So we're going to plug a 5 in place of x in our derivative. I'm going to use brackets instead of parentheses, so I don't have too many. If I put a 5 in, we'll throw that into the calculator. I get negative $3.20. I'm going to think about this as a fraction. I'm going to put it over 1. So we want to remember what we're actually finding. We're finding the difference in the price, or the change in price, how that's affected by the change in demand, the quantity demanded. So our interpretation can be this. If we decrease the price by $3.20, then 1,000 more units would be demanded. Remember, X is given in units of 1,000. So the price being decreased by $3.20 will result in 1,000 more units being demanded. So let's find d prime of 10. I'm going to put 10 in place of x. Okay, I'm going to throw all that into my calculator and I get negative 2.50 over 1. Think about that as a fraction. So change in price divided by change in quantity. So if I'm currently selling 10,000 units, so if 10,000 units are demanded, if at that particular level of demand, if I decrease my price by $2.50, then I will sell 1,000 more units. Okay, d prime of 15, we're going to put 15 in place of x in the derivative. So if I am currently at this level of demand, so 15,000 units are demanded. If we drop the price by $1.40, then 1,000 more units then would be demanded. All right, in this example, we are looking at worldwide box office receipts for a long time running movie, and these receipts are approximated by this function here. So ticket sales, we'll call that T for ticket sales. T of x equals 120x squared divided by x squared plus 4. Ticket sales are measured in millions of dollars, and x represents the number of years since the movie's release. We want to know how fast the total receipts are changing after 1 year, 5 years, and 8 years after its release. We would anticipate that immediately after the release, that the rate of change would be the greatest, that you would be making the most money per year, maybe during the first year of release. Then after that, sales might start to taper off, and you wouldn't be making as much. Your rate of change would not be increasing by as much as the years go by. So let's see if our suspicions are confirmed. If we want to know how fast the total receipts are changing, then we need to find a derivative. We want to find our rate of change formula. We have a fraction, so we're going to use our quotient rule. It will be the denominator, as is, times the derivative of the numerator. So we're going to use the power rule for the derivative of the top there, so that would be 240. So 2 times 120. 240, and then x, and we're going to reduce the power by 1, so we get 240x, minus the numerator as is, times the derivative of the denominator. So just looking at the denominator, the derivative of that would be 2x. All over the denominator as is squared. Okay, we're going to use this to evaluate, so we're going to simplify a little bit here. So if I want to simplify this, I'm going to distribute 240x into the parentheses. So I get 240x cubed, and 240x times 4, I get plus 960x. Then I'm going to multiply these two quantities together. I get negative 240 times x cubed. All of that over the denominator squared. I'm just going to leave that as is. Simplifies quite nicely because we know these two terms would cancel each other out, so I'm left with the reduced form of my derivative. Alright, so we want to know the rate of change. How are the receipts changing after 1 year? So we're going to put a 1 into our derivative to find the rate of change 1 year after the movie's release. So I get 960 divided by 25. So I get 38.4. And remember that we're talking about change in receipts. So the change in ticket prices, or not prices, but ticket sales, divided by the change in the years. Okay. So we can think about this as dt dx. Okay, so change in ticket sales, the receipts brought in, divided by the change in the years. So what do we actually have? How do I interpret this? Well, 38.4, think about that as a fraction, put it over 1, thinking about it in terms of a slope. The change in ticket sales, given in millions, divided by the change in years. So after 1 year the movie has been out, the ticket prices are increasing by $38.4 million per year. So every year we're making $38.4 million. That's our rate of change. Okay, so we anticipate that 5 years after the movie's release that things should be starting to slow down. So let's see what happens if we put a 5 into our derivative. All right, I get 4,800 divided by 841. So I get $5.71 million per year. So now, after 5 years, my ticket sales are only increasing, my receipts are only increasing by $5.7 million per year. So I'm not making as much money per year as I did at the beginning. And what about 10 years, or sorry, 8 years? We said 8 years after the movie's release, how much am I making per year? How fast are those ticket sales changing? So I'm going to put in an 8 in place of x in my derivative. I get 7,680 divided by 4,624, and I get about $1.66 million per year. So that's how much it's increasing at year 8, looking forward there to year 9. So at year 8, I'm only making about $1.66 million per year after 8 years of the movie being released.